Good morning, everyone. Good afternoon, depending on your time zone, where you are. This is Alex Palm. I'm with Berkeley Nucleonics. I'll be co-presenting today with my colleague Stefan Dineden. As you can see, both of our mugs here on the slide. We'll be starting in a few moments. We're allowing more participants to join. We're expecting quite an audience today. Currently, I see about 50 attendees. We're going to give a few more minutes to allow a few late attendees to join before we commence. To the audience who's on board with us currently, we want to encourage questions during the presentation. We will address as many of the questions as we can at the end of the presentation. In your control panel that you're going to see on your dashboard, there is a questions area in a gray bar. Feel free to log any questions during the presentation. We'll review these questions towards the end or at the end. And as I mentioned, we'll address as many as we can during the allotted time slot. More people are trickling in. Again, we'll start here in just a couple more minutes. It's about 10:31 right now, so just a couple more minutes. Allow some last-minute attendees to join. It's good to see a few more people joining us, a couple minutes late. Starting in about 1 minute. Once again, we encourage questions. Gray bar on your control panel there will allow you to ask questions as you think of them. They'll be logged during the presentation, and we'll be reviewing the questions and do our best to get through as many, if not all, that we can at the end. Okay, we're going to go ahead and get started. Once again, I want to thank everybody and give some appreciation for the time that you're going to be investing with us today, learning about our phase noise technology instrumentation. As you can see here on our cover slide and the title of the presentation, Disruptive Phase Noise Measurement Technology, and what we're calling the next evolution of instrumentation. So before we get started, a little bit of an introduction about the company and our organization. We've been a trusted figurehead in test and measurement instrumentation since 1963. Our genesis began with a technology transfer from Lawrence Berkeley National Labs producing pulsars for the nuclear science industry. And over the decades, we have evolved and became noteworthy experts, not only in nuclear technology, nuclear detection, radiation detection, but also test and measurement, as well as RF microwave signal generation and analysis. So BNC, at our core, our mission and what we do essentially is providing our customers with a better experience in using test equipment. And I believe that this presentation is going to really highlight how we do this. And our market philosophy, our engineering MO or mantra, if you will, is to outpackage, outperform, outservice, and outprice all of our competitors in the space. We focus on the advantage of PC-driven instrumentation, and Berkeley Nucleonics is one of the companies in this space that we're on the bleeding edge of changing this paradigm, this disruptive technology. And we're moving away from these large, heavy, cumbersome, complex, fragile, and very expensive traditional or contemporary instrumentation. Instruments, what I mean by that is instruments that have these traditional front panel interfaces, screens, embedded software, disk drives, etc. And by focusing on PC-driven instrumentation, this next evolution of test gear, what we're providing are some key advantages. Obviously, we provide a smaller, lighter, and easily transportable instrument for field use. In addition, we provide a low cost of entry, low cost of ownership, and better long-term reliability. And this would be an obvious statement, of course, but just to highlight on that, that once we remove the liabilities of some of the common failures, like the front panels with all of the components and features that are required to support that, the buttons, the screens, the disk drives, when we remove this all together, we're enhancing long-term and proven long-term reliability. In addition, we provide faster data transfers. So these instruments, all of which you see right here, and this is a nice little example of some of our key instruments in the RF microwave signal generation and analysis. They integrate very well into intranets and sharing domains, collaborative domains. In AT environments, for example, where it's much easier and faster to extract the data, provide the reports, and share it through with your colleagues or cohorts. And that folds into the easier notability as well. And what we mean by notability is that node, that device that can be integrated within a system, within an area. We're showing here our real-time spectrum analyzer, which is an excellent example for that. It's a node that can be placed in the environment to extract spectrum. Feature and performance upgrades that can be launched faster to the market by focusing on the GUI for our control of our instrumentation and removing the PC altogether. We're continually pushing and evolving performance enhancements, feature sets, and better performance essentially. And we launch these to the market and to our customer base for free for the life of your instrument. None of the software that is required or that can be used with our instruments, there is no charge. It's free. You can access from our website. There's no licenses. There's no seats or annual subscription. What's more is that with the releases of new feature sets, you're notified through emails. You can download from our website, but also on our GUI itself, we upload these new feature sets, both firmware and with GUI, with a small button that's indicated on the GUI itself. We upload it to our net servers, and it's a one-click update, very, very quick and painless, but you get these features for the life of the instrument. What's more, we're not locked into an internal PC with an operating system. There's many different types of devices that you can use. So I'm certain that with the audience that we have today, many of you have instruments perhaps in your laboratory there, or in manufacturing, they're using outdated software, perhaps Windows XP 98 or even older for that matter, and that becomes a liability over time. Unsupported, obsolete, you've got issues with virus protection, network issues, firewalls, etc. And in addition, when I say many types of devices, what I'm referring to is the PC. So the PC is augmented over time. We've long surpassed the desktop and even the laptop for that matter. We can deploy our instruments on tablets, even NUCs. It's very malleable in how we can control and interact with our instrumentation. So you're not relegated to this internal PC and managing that over time. And lastly, this type of format, the PC-driven instrumentation, and with our instruments, it's literally designed to resist obsolescence. Once again, I'm sure many of our audience members here have hardware in your labs or in your working space that still use old disk drives, floppy disk drives. That's obsolete. Nobody's using the disk drives. Screens become dim, they can fade, etc. So we're not using that, and again, resistance to obsolescence. So let's move right into our Model 7330 signal source analyzer. This is the flagship product for phase noise testing, and what we will be presenting today. Here's an image of the unit itself. This is a pretty scaled image next to the laptop, so you can see how small and portable, in fact, it is, followed by a ghost image of the GUI, which will be providing some demonstrations as we move forward. So the value that we bring to you, the customer, is a compact, headless, ultra high-end phase noise testing system. And ultra high-end is a very relative statement, but bear with us as we move through the presentation here. We're going to show you what we mean by that and deliver on that promise. We're a one-device solution. Unlike some of our contemporary competitors that require peripheral equipment, down converters, if you will, different instruments for different types of measurements, we're broadband 5 meg to 40 gigahertz in one box, as you see in front of you right now, turnkey. We provide both additive and absolute phase noise measurements. Additive is for, of course, non-self-oscillating devices. Absolute is for self-oscillating devices, oscillators, etc. In addition to this, we provide a very good tool set to measure many different types of DUTs, and we're going to highlight these as we move forward as well. I mentioned earlier free updates for the life of the instrumentation. And another very important attribute that we bring to our customers is the ease of maintenance. So we provide various calibration resources. We're one of the few companies that actually sells a certified noise standard that we can provide to our customers, as well as the calibration procedure, which is automated. It's a built-in procedure, and you can calibrate in-house or use any third party that you wish. And of course, BNC calibrates our own instrumentation very quickly in-house. And lastly, to bookend our value-add proposition here as a whole, we are a fraction of the cost of contemporary or traditional instrumentation, and we're going to show this as we move again further through the presentation. But we offer tremendous value just at the dollar level, where we are a third of the cost of many instruments, if not more. So why is phase noise increasingly important? I'm going to now hand over the reins to my colleague Stefan, who's going to give you all the details that you'd want to know and perhaps more. And without further ado, Stefan, it's all yours.
Thank you, Alex, and welcome everyone to this webinar from my side as well. Now, before we look at what phase noise is and how we can measure it, we need to look at why this is important. Faster information transfer has always been a driving force in the RF market, but higher data rates in communication systems fundamentally limit the energy per bit of transmitted information. Less signal energy results in a lower signal-to-noise ratio, which we don't want, of course. So since we want to have the signal-to-noise ratio stay at the same to ensure no degradation for transfer protocols, phase and amplitude noise requirements get continuously more challenging. This causes tighter system margins, which demand for phase noise testing in both production and development. So this is the basic reason why we need to care about phase noise more and more. Now that we are at the point where we want to measure phase noise, we need to know what it actually is. So I give you a short introduction into phase noise. Some of you might already know this. It's going to be quite short. An ideal oscillator, like you see on the right side, the power spectral density, would generate a pure sine wave. If you look at the power spectral density of an ideal oscillator, it has only energy components in the carrier frequency itself. So it is represented as a single direct pulse. Of course, in reality, this is not achievable. Besides the carrier frequency component itself, real-world oscillators always cause noise contributions to the sidebands. The eye diagram on the left side shows an example of those fluctuations in the time domain. And the power density plot on the right side shows the same effect in the frequency domain. So we have these noise contributions in the sideband that you can see there. In the time domain graph on the right side, you can see how phase noise is fundamentally describing the statistical distribution of the zero crossings of a waveform when compared to its ideal counterpart. You can also see that in the eye diagram, of course. This noise is usually represented as the power spectral density of the single sideband in the frequency domain. The noise contributions can be separated into phase fluctuations as well as amplitude fluctuations of the signal. The phase fluctuations are commonly referred to as phase noise, and it's what we're going to focus on today. They're also called jitter if you look at them in the time domain, and the amplitude fluctuations are referred to as amplitude noise. So let's look at the first demonstration here with a very simple measurement of a continuous waveform. I have a little schematic here. It's a very simple one because we just have hooked up a signal generator to one of the signal source analyzers. So if we change over to the graphical user interface, we can see that the graphical user interface or the instrument itself has already detected the signal. We have a 10 gigahertz signal at roughly 0 dBm. There is some loss because of the cable. So as we already detected the signal, we can just start the measurement, and then we can look at what the phase noise plot actually looks like. So the measurement has started, and here the first few correlations are coming in. You can see on the x-axis the offset frequency to the carrier. So all on the left side somewhere would be the carrier, and the further to the right we go, the more away we get from the carrier in the frequency offset. And on the y-axis, of course, you see the single sideband phase noise, described as usually in dBc per hertz, which is decibels relative to the carrier at a 1 hertz bandwidth. All right, so if we go back to the presentation, now I want to quickly mention where phase noise in a DUT is coming from. There are many contributions, but the three most common sources are listed here, especially for like random noises. So we have random and we have deterministic sources. The random sources are thermal noise, which are temperature fluctuations. They're caused by the Brownian motion of electrons due to thermal agitations of the electrons. Shot noise is a quantization effect, so it's coming from quantum mechanics effects, and it's caused by this continuous current flow across potential barriers. And last but not least, the flicker noise is spectrally related to the 1/f and found in all active devices and even in some of the passive devices. Besides these random sources, there are also deterministic noise sources, including hum noise, which is basically power supply feed-through. In America, this is usually at 60 Hertz and it's harmonics. In Europe and most other parts of the world, it's 50 Hertz. Then we have spurious signals, and we also have, for instance, resonances, like in quartz crystal oscillators. Now that we know what phase noise is and where it is coming from, let's try to measure it. There are a few methods of measuring phase noise. We have listed here the two most commonly used devices, a spectrum analyzer and a dedicated signal source analyzer. Let's first look at the spectrum analyzer. Of course, the big advantage here is that a spectrum analyzer is usually already available in almost all labs that deal with high-frequency signals. Some of the spectrum analyzers already have a phase noise mode included, so you can select phase noise in the user interface, and it's quite easy to perform a measurement on your DUT. On the other side, there are also disadvantages. There are severe limitations in dynamic range. So for a typical spectrum analyzer, this lies about, you can measure down to about -145 dBc per hertz, depending on your spectrum analyzer, of course. And there are also limitations on close-in phase noise. So phase noise that has very low offset frequencies, that is very close to the carrier, because the local oscillator and the resolution bandwidth of the spectrum analyzer limit this measurement. Another disadvantage is that a spectrum analyzer cannot distinguish between amplitude and phase noise. This is because it basically just looks at the spectral power density, the power spectral density of a signal. So there is no way to figure out where this noise is actually coming from. Another important restriction is the DUT frequency stability is severely restricted when you measure with a spectrum analyzer, because if your DUT is changing frequency during the measurement too far, this will directly distort the measurement result. And there is no way around that with a traditional spectrum analyzer. A dedicated signal source analyzer, on the other hand, is built for phase noise analysis. Disadvantage usually is that you don't have one present when you start thinking about phase noise, unless phase noise has already been a concern in a previous project. But it also has a bunch of advantages. Probably the most prominent one is the high dynamic range. So you can do measurements down to -185 dBc per hertz, for instance, in the BNC signal source analyzer example. And it also has the capability to distinguish between phase noise contributions and amplitude noise contributions. It can measure phase noise very close to the carrier itself. And it's possible to measure DUTs that are very low noise, DUTs that are very drifty, or frequency-wise very unstable. And you can even measure modulated signals, like signals with a pulse modulation or a frequency modulation on top of it. So it's a great tool set for signal source analysis. So if we go back to our example from before, we had this 10 gigahertz frequency signal from our signal generator. I have now activated a frequency modulation on top of this. And as you can see, we can still measure this. So we still have a valid measurement going on. This would not be a reliable measurement with a spectrum analyzer, or even with a phase noise analyzer that only uses a pure PLL design. At the moment, the system is using IQ demodulation to do this measurement, so we can actually track the signal digitally. We can also look at the same signal in a spectral representation here. This was automatically done while I did the other measurement. So you can see the spectral distribution of my frequency modulation. And another way that we can actually look at this signal is with a transient analyzer, which allows us to basically demodulate the signal in the time domain. You can see the sine wave modulation directly in this frequency versus time plot on the right side. And if I change the modulation, you can see a direct impact if we make it stronger or less strong, if we change the frequency here, or even if we change the shape of the modulation. So I change now to triangle modulation, now back to sine modulation. So this is a very interesting tool if you want to look at modulated signals, for instance, or also if you want to look at sweeps or chirps, just any kind of frequency changing signal. All right, let's go back to the presentation now. So as I mentioned before, there are many DUTs that can be measured with a dedicated signal source analyzer. So we have on the one side very low noise
So it seems as though Stefan had lost his connection, unfortunately. I'm sure he'll be logging back on here in just a second. So what we're referencing here is the multitude of DUTs in which we can measure. VCOs, YIGs, and I'll bring up the YIG for that matter, that they're notorious for instability in terms of frequency and then drift, or perhaps voltage-controlled VCOs. We have proven excellence in being able to lock and measure these types of devices better than any other system that we've been able to examine or compare to. So once again, the multitude of DUTs is diverse with our instrument. We work with some of the more challenging devices that are out there. And in fact, we have a dedicated mode specifically in our instrument for unstable and drifting sources.
All right, Alex, I think I'm back again.
Very good. All yours.
Sorry for this interruption. All right. So how does our BNC signal source analyzer actually measure phase noise? In one single phrase, we can say that phase fluctuations of the DUT are converted into voltage, which is then filtered, digitized, and post-processed to derive SSB phase noise, or single sideband phase noise. If we look at this a little bit more closely, the signal is first down-converted with a local oscillator. Depending on the DUT type, as Alex mentioned just before already, we can use different measurement modes to cope with that. So for unstable measurements or for unstable DUTs, we use a different measurement mode than for very stable DUTs. So one of three methods is used in this case. We have a direct conversion method, and then we have heterodyne and dual heterodyne methods where we have a two-step down conversion. The resulting baseband signal is then amplified, filtered, and digitized. And this is followed by a digital processing step. In the case of the BNC signal source analyzer, this is done on an FPGA on board of the instrument. This also includes part of the post-processing and statistical analysis already. And finally, the graphical user interface that you saw before is used for visualization and provides further tools for statistical analysis and post-processing. So on the left side, you can see a diagram showing the principal components of a standard phase noise measurement with the signal source analyzer of BNC. So this would be a single heterodyne design. You can see the two channels. So we have a channel at the top, and then we also have a channel at the bottom. Those are basically duplicated hardware inside our instrument that are physically separated from each other. So there is no noise interaction or interaction in general between those two. This allows to do this measurement parallel twice at the same time, and then in the end merge them with cross-correlation techniques. This gets rid of a lot of unnecessary noise, basically. So noise from the reference, thermal noise from our systems will be able to overcome with this method because they are basically uncorrelated since we have physically separated them from each other. And another thing you can see in this diagram is this PLL, so the phase-locked loop here, that makes the reference track the frequency of the DUT. This is actually the part that allows us to down-convert the DUT signal directly into voltage that represents phase noise. In terms of applications, the BNC signal source analyzer provides a wide tool set containing, of course, absolute and additive phase and amplitude noise. We can measure signals both of the type of continuous waveforms or also modulated signals, pulse modulation, frequency modulation, etc. It provides a transient analysis mode that allows to demodulate the signal or look at very fast frequency transients. You have already seen that before. It features a cross-spectrum baseband analyzer, and it also functions as a test bench for VCO characterization. So let's look at this VCO characterization quickly. We have already prepared another demo where I've set up a VCO with our system. So as you can see, we have connected basically the supply port, the control voltage port, and the RF out of the VCO to the BNC system. And now if we go to the graphical user interface again, we see there is a VCO characterization tab at the top. I have already selected that. I've also already selected the supply voltage to 5 volt and the tune voltage range to 0 to 5 volt, which is in this case the tune range of this VCO. So if we want to measure without phase noise, we can just quickly start it, and you will see the measurement itself will come up quite fast. We have a characterization of frequency on the top left. We have tuning sensitivity, power level, supply current consumption, and supply pushing, everything plotted against tune voltage. We can, of course, also include phase noise offsets here. So I've selected 4 offset frequencies of 1 kilohertz up to 10 megahertz. And if we do this measurement, it, of course, takes a little bit longer because it has to measure the phase noise at every single tune voltage. But you can see slowly the measurement is also coming up here and plotting the single sideband phase noise at the specified offsets here. All right, let's go back to the presentation now again. I also want to spend a minute to talk about automated testing, because I think that quite a few of the attendees are actually coming from this field. This is an application that more and more includes the parameters of phase noise into the process because of basically the arguments that were mentioned in the beginning of the presentation, where I talked about why phase noise is actually important or is becoming more and more important. So the BNC signal source analyzers offers a throughput optimized solution that can reach measurement speeds of 100 milliseconds per DUT or even below. depending on your requirements, of course. On the right side, you can actually see the basic trade-off curves of accuracy versus measurement time for a typical ATE measurement with the BNC signal source analyzer. So you see, if we spend very little time on the measurement itself, the accuracy is higher. So if, for instance, you're only interested in spot noise of 1 megahertz or above, a measurement time of about 80 milliseconds is already quite sufficient and gives you a good accuracy on your 1 megahertz offset. But on the other side, if you're interested in offsets that are closer to the carrier, like 10 kilohertz, for instance, you would need to have or invest a little bit more time into the measurement. So in this case, probably about 150 milliseconds measurement time would already be good enough for the requirements. And if you add the 1 kilohertz spot as well, you would probably go to 200 to maybe 300 milliseconds measurement time and still have a very good accuracy. All right, so this concludes the technical explanation of phase noise and our current signal source analyzers. I will give over the controls back to Alex, who will look at an industry comparison between the solutions that are currently available.
Sorry, everybody. Sorry for the glitch there. Apparently, I was muted. So, no, I'm not. So, once again, Stefan, thanks for the technical insight that you were able to provide to the audience today. And as Stefan had mentioned, this is an industry comparison which is very broad, but highlights some of the more common instruments you'll find in the industries which our customers have relied on in the years past. You'll notice that this is, as best as we can, is an apples-to-apples type of comparison with frequency range, offset ranges. Some devices can provide some of the measurements that we can do, some can't. For instance, pulse measurement, additive noise, or AM noise measurements as well. But one real nice highlight in here, of course, and something I mentioned in the beginning of the presentation, is the cost that we bring to the benefit to our customers. It's nothing that we lead with, because we don't want to be a low-cost alternative for these other devices and to our customers. We offer really, I think, important, cogent advantages technically and performance-wise over the competition, and then the lower cost is just an excellent bonus. We'll be providing this presentation to the audience thereafter, and we have more granular industry comparison charts that we can provide to you in addition to this. So in summary, our value proposition to you, the customer, how this is disruptive to the status quo that's out there, and I know it's cliche to say it, but it is a bit of a paradigm shift in terms of phase noise capability, the instrumentation, and how we provide these measurements. So as a recap, we are providing a all-in-one instrument. We cover all of your it's broadband and all of your analysis and frequency range from 5 megs to 40 gigahertz. So low cost of entry, we noticed this on the previous slide in terms of the cost per unit. The low cost of ownership, the no charge for the software. In addition to this, and one thing that hasn't been mentioned yet is we have a rich library of APIs in addition to the GUI. Everything is Skippy compliant as well. For instance, with the APIs, we have NI certified LabVIEW drivers, MATLAB example, C++, etc. Low cost of ownership with the calibration that we highlighted earlier, and also the longevity. We're removing the liabilities of some of the failure points of these instruments. We also reduce the complexity of the hardware and of the measurement itself. A highlight or an example that I'll provide to the audience right now is with our pulse measurement capabilities. one measurement technique that wasn't highlighted in the presentation today. But what we've done is provided an extraordinarily simple way to measure pulse measurements. It's simply a checkmark box in the GUI. By comparison, some of the other instruments that are out there require racks of instruments, very or large space, numbers of instruments. It's highly complex to set up. We've reduced that complexity tremendously and made it extremely simple to use. What's more is that with our GUI, and we didn't really highlight some of the added features, the ease of use today, we can certainly provide this to our customers on an individual basis. But the focus of our design work in the GUI itself was to make it as powerful as possible, but as intuitive and easy to use as possible. In every literal sense, somebody that has very little, if no experience doing phase noise measurements can now get on our instrument and with very little guidance can be conducting phase noise measurements in a matter of minutes. We've sort of self-coined the term the one-click measurement. And I tend to refer to it loosely as the technology onion, so to speak. So very straightforward, easy to use, but our post-processing capabilities are deep. We can pull back those layers and give you data and reports in various fashions at a click of a button. We can set spec lines for testing or with ATE environments, changing shades and colors. So it gets much deeper than that, but again, very easy to use. We offer some of the fastest analysis times in the industry, which effectively can increase yield in production environments. And we're happy to share some additional data sets that we provide that have been conducted independently by comparison to some of these other instruments that we've even shown today in our comparison chart. We've reduced the measurement times by more than half of some of our competitors that are out there. So it could be a tremendous advantage in production environments. In addition, we're extremely versatile, so clearly we're portable. We offer DC input. It's rack mountable, it's benchtop capable, of course, and mention our AT implementation. Now the DC input is something that I'll come back to just highlight for a moment. There's two additional advantages to this. One is that with its portability, it can be used out in the field. So we have our instruments being used on ships, aircraft, out in harsh environments, satellite uplink down stations. So we can, with the DC input, we can use external rechargeable batteries to power the device. And with that, if you're working in a very noisy environment, very dirty environment, we can eliminate the issue with line contamination and pollution. So you can run the instrument from a universal power supply or a battery itself. And lastly, this is something that I really want to bolster and highlight to you, the audience, is that we believe that we offer an unparalleled customer service experience. Anybody can sell a product, but it's the customer service that the company stands behind that really determines its success. Many of the customers that we've worked with lament about these arduous processes to get customer service where you have to file a ticket support, or support ticket, I should say, just for basic questions, perhaps operation, or if you need calibration and repair. You don't have to wait for somebody to call you back. We get you in touch with applications engineers in real time. What's more is that with our customers, if for any reason you're down, we can and will overnight instruments to you to keep you up and running, particularly important again in AT environments. We're not worried about did you drop it, whose fault was it. We ship the units and then worry about that later. We want to keep you up and running. Our lead times are very short. We can offer as low as 2-week lead times on many of our deliveries. Like I said, we get you in touch with applications engineers off the bat if you have any applications-oriented related questions. So, in effect, this has been our brief presentation today. We've kept it to about 40-45 minutes. We didn't want to get too dense. We want to give you a good overview and why, in fact, we believe that this isn't disruptive, and why we believe that it's one of the best, if not the best, phase noise testing systems that are on the market and available today for all the attributes that we've shown to you. So we will address a few questions that have come in. Bear with me one second. We've had some good technical questions and some general questions. I'm going to address a few of these questions right off the bat and defer a few of these to my colleague, Stefan. Some of the more basic ones and easy ones to answer are, do we provide demo units? And the answer is naturally yes. We're happy to work with you on that. Just get in touch with our team, info@berkeleynucleonics.com. You can reference our website, our 1-800 number. There's various ways to get in touch with us, but we're happy to work with you in demo-oriented situations. There was a general question that was also asked, and easy to answer as well. Somebody asked about the gray shaded area under the trace on the GUI itself. And quickly, not to get too technical, but that's a very nice visual feature that some of our competitors do not offer, essentially showing you the relative noise floor for that measurement. It's a great way to understand if more correlations are needed or if you're getting the best sensitivity for that measurement. So it really increases the productivity. Doesn't leave you wondering, should I increase my correlations to get better sensitivity? If you have a nice separation on the gray shaded area to your trace, you know you're getting good performance. There's another question that's a little bit direct in terms of the competition, but somebody wanted to know how we compare to the 5052. And that's a great question, because the 5052 is really the sort of an industry standard in terms of just pure numbers of units that are in laboratories. People tend to refer to them as the gold standard, if you will. So recognizing this, we've taken some painstaking efforts to independently verify our sensitivity directly to the 5052, and we have reports that we can provide to our customers to show as good a sensitivity, if not better. So it shows direct correlation in terms of the measurement capabilities. What's more is that we can improve the sensitivity over the 5052 with some of the features and options that they do not have. For instance, our ultra-low noise internal references. Let's see here. Stefan, do you want to tackle some of these questions that you're able to see the question?
Yeah, I can, yeah.
Why don't, there's some more technical ones in here. I think that you'd be best to address some of these if you don't mind.
All right. Yeah, so one of the questions was, or actually there were a few questions about additive phase noise, or phase noise of non-oscillating sources. So one of the questions was, can system measure minus 170 dBc per hertz at 10 gigahertz on a driver amplifier at 10, 20, or 30 gigahertz? So the answer basically is yes. The system noise floor is way below that. The only restriction that you have in your setup is basically the local oscillator that you're using, or the oscillator that you're using for your measurement. So I can quickly show you, if I can take over the presentation here again. One second. All right, so I'm just sharing at the moment a basic diagram of a setup, of a measurement setup with an additive phase noise measurement. So the DUT is something that is not oscillating by itself. In the instance of this question, it is an amplifier. So you have a local oscillator that goes into a power splitter. So this is for a one-channel measurement. And then you have two separate channels, one with a phase shifter and one with a DUT, with the DUT. So the DUT and the phase shifter can be on wherever side they want to be. They just need to be on one of the two channels and not on both of them. So the limiting factor here, usually, at least with higher frequency, is the oscillator itself. So there is a very good neutralization of phase noise of this oscillator with this method. On the other side, there is not a great neutralization of amplitude noise. So your local oscillator needs to be quite well in amplitude noise in order to get down to those levels. This can be circumvented partly if you switch to a two-channel measurement, so a cross-correlated measurement, where you would need an additional shifter and an additional power splitter. So this is basically the answer to this question is yes, it can be measured, and we can also help you with the setup if you need that. Another question was for VCO characterization, what is the minimum step size for the voltages? So the tune voltages mostly, I would say. The supply voltages, they can be set down to 50 millivolts accuracy. The tune voltages, they can step through with an accuracy of about 10 millivolt. So you can have quite a high resolution in your tuning range if you want that. Although the measurement will take longer, of course. Another question that we had was in direct conversion mode, do you provide high resolution frequency counting and Allen deviation analysis? The answer is yes, we do. We can. You can actually, with the transient measure mode, you can also use this to do very long-term frequency measurements. Frequency measurements that take hours, days, or even a week or so. And then you can look at the long-term frequency stability analysis, which is basically Allen deviation. Another question is a more general one. Is there any specific software needs to be installed before one can use the GUI shown, or the graphical user interface shown? The answer is yes, this is a Java-based graphical user interface, so you would need to have a running Java runtime. This, of course, means that it is not restricted on Windows, because Java runtimes are also available for other platforms like Linux. So you do need a Java runtime, but that's the only restriction that you have.
Stefan, can I add a point to that?
Yeah, sure.
Very good. One thing that might be noteworthy is that with PC-driven instrumentation, we're not doing any of the processing power within the PC which you choose to use. All of the data crunching, the processing power is done within our instrument, and what you're seeing on the GUI itself is simply a translation of that information. So regardless of the computer that you choose to use, you're going to get the same performance from our phase noise test system, given that you have adequate performance with basic performance within your PC, and that's delineated out in our manual itself.
Okay. So there were a bunch of questions about specifications. I think there will be a follow-up mail to all the attendees where we can, of course, also include the data sheets where at least all the questions I saw so far regarding specifications are answered in the data sheet there as well.
Correct. What's more is that we have a log of all the questions that have been asked. If there's anything that we haven't been able to cover on the call today, or if it becomes more specific, we'll be sure to reach out to you individually and answer those questions for you. What's more is that if you think of any additional questions after the presentation, please get in touch with us. We encourage that. If you're interested in any, as we mentioned earlier, demos, data sheets, or perhaps even any quoting for budgetary purposes, please feel free to get in touch with us. Our 800 number is listed on the presentation here. You can also reach us at info@berkeleynucleonics.com. So with all of this, once again, the PowerPoint will be sent over to you, as well as a recording of the presentation given today. We hope that this has been informative. We look forward to working with you additionally for any projects, any upcoming requirements you might have in phase noise testing, any ideas, any feedback for us that you have in terms of improvements to the system. Perhaps some of you have some experience using our instruments. We welcome that as well. Very much appreciate everybody's attendance today and your time and your consideration. Without further ado, we're going to conclude the presentation. Everybody else, please have a great rest of your day.